Today we will talk about emulation of complex systems, embedded systems. Previous demo, we have discussed the co-simulation of hardware and software, so we're not going to talk too much about that, but we are going to focus more on the applications and virtual I/O this time. Emulation as a concept is to emulate the real system using a computer hosting platform, and it can emulate CPU such as ARM, PowerPC, DSP, and others, or complex logic like those that you implement in FPGA or embedded FPGA or in a real ASIC, and also cores or IP cores or accelerators or peripherals. Embedded systems typically have many different I/O peripherals to allow it to connect to the real world. So embedded system and emulation system of embedded systems allow you to exercise real software and real hardware code. And what that does is it saves time and resources and lowers the development cost, eliminate the dependency on expensive or not yet existed hardware. For example, if you develop subsystems for airplanes, you would have a very hard time to get a hold of an airplane. Or if you're developing chips, that chip may not exist for many, many months down the line. And you want to do your testings and things ahead of time, which would increase your quality and reliability, and emulation system allow you to do that. Here is a typical diagram of a embedded system where on the left-hand side you have CPUs and then complex logic maybe in the middle here and a lot of peripherals on this side. And this allows you to run real application with real-time data. So the way we do the emulation system is we divide it up into 3 segments. On the left-hand side, you see the CPU here, which we use the quick emulator to do the emulation of it. And for the logic and the cores, we use the SystemC simulator to emulate those functions that allow you to exercise real RTL code, such as Verilog or VHDL. And on the right-hand side are the physical I/O. Emulating the physical I/O is much harder. So we develop a concept called virtual I/O to do that. And all of these emulation is running on top of a Linux PC computer host platform. The demonstration today, we have implemented a gateway or wireless gateway system emulated on a computer system. And so on the left-hand side, we create the wireless network, and various devices such as smartphone, laptop, or embedded Linux client can be connected to the gateway system through wireless network. For the demo, we will use a laptop on this side. And for the connection back to the internet, we allow it to connect out to the Ethernet. In the future, we'll add more I/O, such as for motor controls and sensors. So in terms of the software in the system, if you look at the top here, this will emulate the CPU, so it runs things like the Linux operating system, the device drivers, and it runs our integrated proxy on it. And the hardware, such as the Ethernet controller and stuff, run in SystemC emulation. The virtual I/O layer, which is the third layer here, allow you to connect back out to the real world using the host I/O. So in the computer system, there are various I/O available, or you can add additional cards into the system to create more I/O that you can connect to real life. And through the virtual I/O layer, the emulations platform or emulation system, which is on the top here, can connect to the real I/O below through the virtual I/O. So a system like this, which is a gateway, typically they can be used in the air vehicle or ground vehicles, and these are some of the potential applications that can be used. So people that are on the ground can communicate to other kind of systems or network via the gateway systems. So without further delay, I will let Karate and Sunny tell you more about the actual working of it.
So the first thing that I will do here is set up my wireless hotspot so that different wireless devices can be connected to this system. To set up the wireless hotspot, I will need IP address and also the interface name. So I'm just setting up my wireless hotspot. And I'll provide the IP address and interface name. It is asking me to name my network, which I'll give as LL738X, and also create the password for the same. As you can see that we have successfully created the wireless hotspot. Now different wireless devices can be connected to this system. After that, you can see three different terminal windows on the screen. The leftmost window is running QEMU on the Linux host. I have already booted up, and in our previous videos we have explained the booting process in detail. I will log in as root and bring up my Ethernet port on the QEMU system.
So this is the Ethernet port on the emulated environment.
Right. Next, I will run my user app on the QEMU system. So my user app is running on QEMU right now. The second window, the one in the middle, is used for compiling and running the programmable logic, which is mainly written in SystemC.
And Verilog and things like that, right?
Right. The last window, I'll be running my TCP server, which will communicate with the wireless devices and receive packets from the wireless devices and also forward them to the QEMU system. So to run my TCP server, I'll provide a port number as an argument. As you can see, the TCP server is running on IP address 10.42.0.1 and with the TCP port number as 12,000.
So all the wireless client, if they want to go through the gateway, they go through TCP port 12,000.
Right. Next, I'll also bring up the Wireshark so that later we can compare live traffic from the wireless device and on this system. Kirate will explain the setup on wireless device and also show how we can access different websites through QEMU.
So we are currently on the wireless client side. So the first thing to do here is to connect to the wireless network. So this is the wireless network that Sunny had just created. Now I already pre-configured the proxy settings for the browser to make sure that our data goes through the wireless gateway, and to make sure that we are not loading anything from the cookies and cache, I will just clear everything in the browser settings. The first website that we will try to access is google.com. So I will clear everything on the Wireshark to capture the live data. The user app is already running on the Linux system, so we are able to see the Google homepage. Now we will try to surf through internet. So I will try to make some search on Google. Here are the Google search results for Yosemite. So as we can see, it is trying to load the images.
So images has a lot of data,
Yes.
and right now you are on the wireless client. It go through the wireless network,
Yes.
and then it go through the gateway,
Yes.
which is an emulated gateway, and then on the other side, and it go through the Ethernet, go out to the internet side.
Right. So it is able to load images, and I will also try to play a video in this link. So we'll try to access the nationalparkservices.gov website. The Wireshark here is capturing the live data, which we will use to compare it with the data on the remote side with the help of Wireshark. So there is some pop-up over here. So as we can see, it had loaded several images and almost the entire web page. So there must be some video in this link. Maybe in the Yosemite Nature Notes. As we can see, there are several videos on this page.
It seemed to load fairly quickly.
Yes. And there are few more videos on this page. So we'll try to play one video for this black bears. This page seemed to be loaded completely. Now in the next part, we'll try to compare the data on both the Wireshark, one on the wireless client side and one on the remote side, and we'll try to prove that data is going through the wireless gateway. So let's switch to that part.
So we are back on the Linux host system on which the QEMU is currently running. As we can see on screen, the left hand side terminal window shows some connect requests to multiple websites such as google.com and other websites that are running behind when we try to access google.com. And also you can see that TCP server is still running and the programmable logic window is also up. Now whenever we try to access a different website, we saw some connect requests such as www.google.com, and we are printing some data for comparison purposes. Now whenever Kirate tried to access a Yosemite website, National Park Services, here we can see that it is connected to www.nps.gov. Next, I'll bring up the Wireshark captured file on wireless device and also on the Linux host. So the left hand side Wireshark window is from the wireless device, that is Windows operating system, and on the right hand side is the Wireshark file captured on Linux host, and the terminal window in between is of the QEMU. Now as we can see on the left hand side of the screen that we get connect request for www.google.com, and from the server we receive 200 OK response. After that the client is sending some client hello data to the remote server. Now for the client hello data, if we compare the TCP payload, then we can see that first 16 bytes are 160301, 16.03.01, and similar data we can see on the QEMU terminal window. Now we will check that whether we get the same data on Linux host Wireshark file. So here I go to Wireshark capture on the Linux and click on the client hello message, and we will check the TCP payload data. So here also we will compare, and we can see that we are getting same data as 1603.01.02.00.01.00.01. So this is the flow from wireless client wireless device to the remote server.
Okay.
Now
Hold on 1 second. Sir. So you trying to show that the wireless client is a Windows system and the emulated system is a Linux system, right?
yeah, right.
And you have transported the Wireshark capture so that you can do the show side by side.
Right. So for the comparison purpose, I transferred Wireshark file on the Linux system.
Okay, so now you completely on the Linux system.
Right.
Okay.
And now we are comparing the data from remote server to the wireless device. So here we receive server hello response from the remote, and that response will go all the way to the wireless device. We will also compare TCP payload bytes from the remote server. So we can see that the first 8 bytes are 16, 0300, 0300, 7A02, 0000, and the same server hello server hello packet we receive on the wireless device Wireshark file, and we'll also compare the TCP payload over here, which is 16.03.00.7A02.00.
Okay. So this every time the connection is open, this is a encrypted path. So it trying to do a client hello and server hello, and the packet that you just show is the server hello coming back from the google.com back to the client.
Right, yeah. So we are getting server hello from google.com.
Okay.
And thus we can prove that the data is going through the QEMU emulator to the remote servers such as google.com and coming back from them.
So you show data that go from the Ethernet port, going into your QEMU, and your QEMU print the data out to prove that the data in fact go through the emulated system, and then it went all the way back over to the wireless client side, which is the Windows side,
Right. Yeah.
on the other Wireshark capture.
Right. And also I'll show you the GTK wave like waveforms we captured during the operation. We pre-captured this waveform, and whatever data we receive from wireless client wireless device goes through our LMAC XDMI TXT and goes out to the remote server, and whatever data we receive from the remote server comes in on the XGMI RxD port, and then it goes all the way to the wireless client device.
Okay, so the intention here is showing the way that you capture from your Verilog.
Yeah, from our RTL code.
Okay,
RTL
so this
value
is the
code.
SystemC stuff.
Right. Yeah.
Okay, and you show that the packet actually go in through the SystemC RTL code and go out to the Ethernet.
Yeah.
Okay.
Exactly.
The team demonstrated emulation technology, and they show a use of mixed computing technology for supporting CPU, RTL code, C code, etc. So they use a gateway application as a demo, and through virtual I/O technology, they show you the access to wireless network concurrently with the Ethernet network, and it's running with real hardware and software code using real data that are in real time. So thank you very much for watching.